Greetings, gentle readers, fellow earthlings. April 22, 2026. Reading Foundations today with Ross Finlayson, myself. The recent installments of these video essays have been about quantum dynamics. After the doubly objective relativity theory bit and relative space for the space frames and frame spaces. Then there's been about the quantum commutators after the rational radical and algebras and magmas, and the accounts then of the quantum commutators was a consideration about what the Planck constant is, and as after an account of reduction and reductionism. And the severe abstraction of here the electronic reduction vis-a-vis the mechanical reduction and mechanical abstraction. That's the account, usually the energy and the entelechy and these kinds of things. And the theory, they call it physics. It's a field theory. It's a gauge theory. It's a relativistic theory in the mathematical treatment and account, but it's more of a continuum mechanics in the overall causality of the things. The quantum mechanics often introduces that there's indeterminism. And one way to look at that is that all we have is statistics to measure the things by. And so arbitrarily, that's the same thing as saying there's a scientific hypothesis and there's a statistical hypothesis. And then as with regards to the actual behavior of particles, if these even exist, the particle conceit of waves or structures or the overall continuum of things, it's a continuum mechanics. And so the indeterministic nature of quantum mechanics is usually given as part of the theory after the Copenhagen conference, when after the atomic physics and the old quantum physics, and there came to be kind of this colloquium of the greatest scientists, physicists, quantum physicists in the world, saying that what we're going to do is we're going to have it be statistical. And so the quantum amplitudes are kind of what are given to describe for then the formalism in the Hamiltonian, which is otherwise the account is after mechanics and since the Galilean and all this kind of thing. That then the quantum amplitudes then usually are given as for the bracket or the bracket, with in the middle of that being some kind of constant, and then the expectation bar is bra pipe cat that pipe or vertical line segment being the expectation bar is based upon usually enough of the Bayesian as well. It gets involved with that. And then the account of the quantum amplitudes is that they're, as after an account of Hilbert space, which is kind of like Minkowski space, but it's complex numbers. So it's really just not the real vector space. It's a complex space. It's just the complex diagram sitting on the R squared, the real plane. So that then the amplitudes add up after squaring them and about the roots of the amplitudes, as why the distribution would be a probabilistic distribution, meaning the area under this curve equals 1. And so between 0 and 1, if you pick a random number, it's basically picking a point in that curve. And then how that would be is according to the shape and scale parameters of distributions, how theory of probability has it, so that the statistics and the statistical hypotheses and then the scientific hypotheses are reasonably enough, because there's not rather the mechanics, the mathematics of the continuum mechanics that would otherwise give how these convergences and emergences result for things like something that spins infinitely fast, or as the account of the Bohmian wave, that it happens in the non-local, meaning it's extra-local, meaning that instead of things happening at only one place at once, they happen as, of course, of a region. When in the particle conceit, that could only be a point, but in a wider region, the account of the pilot wave of Bohm is the idea that when there's the idea of a particle that then actually when that makes a collision, according to a detector, that the emitter would make the event arrive to the detector, that the event so described as by a particle would actually be the coalescing of this particle as from a wave that, unlike the usual ideas of water waves, it kind of collapses everywhere at once. It breaks everywhere at once instead of at a single given point in the usual ideas of these things. So it's non-classical, it's super-classical to otherwise give a deterministic account to the objects of quantum mechanics by their behavior, according to the sampling, measurement, and observation effects, those being interferences with the system. To introduce a detector in the system has now that it's taking part in the interactions themselves. That thusly we can have more of a deterministic account of quantum mechanics than an indeterministic account. And then that's okay with our statistical interpretation and our scientific interpretation, and then also about things like the Heisenberg uncertainty, which is made an account of about the electron and the uncertainty of its position or momentum in its measurement, not in its state, because it has position and it has momentum, but then about the measurement that it's involved with the sampling, measurement, and observation effects, and then also with the fact that as the idea of what it is a finite quantity in a particle, is that it would otherwise have to be this continuous sort of nature, and even in the oscillating vis-a-vis the account of these quantities is fixed. So part of the Heisenberg indeterminacy is according to the measurement and the idea that measurement is imprecise itself, and so that's the usual account that people would grasp is saying this, like I could never get this perfect quantity when it's supposed to be some fixed quantity, this quantum quantity. Then the other idea here is also about the fact that, well, if it was never really like the lowest energy level electron or the innermost shell of these orbitals, and the ideas of things like about as the formalizations are made of these, that after the Copenhagen conference, then there was kind of the solvayers for Born and Pauli, and that being the way that quantum mechanics is given, when there are others like Bohm and after de Broglie and this kind of thing. That's then a way to help avoid the fragmentation of a kind of a pluralistic notion of accounts when there can still be one account. And then just like the idea is that reason needs an intersubjective account because any two individuals have their own opinions as about whether they see the same things, as how light behaves and these kinds of things. Like optical light is special. And then with regards to these other abstractions, the reductions, and then to the quanta and about the relation of photons and electrons, and then everything kind of follows as after the measurement of electrons, but not really just their charge, but always their charge-mass ratio, and that always varies itself as a quantity. Super-classical, asymptotically free, the accounts, when they're anti-inductive, yet they can still be seen to hold all together well. That the energy then is in the entelechy, E-N-T-E-L-E-C-H-Y, entelechy. And then for that being a thorough sort of account where continuity law, it brings conservation law and invariant theory, and then as for where the principle of inverse brings excluded middle or non-contradiction, and the principle of thorough reason, sufficient and thorough reason, brings the principle of sufficient reason, that then these continuum mechanics bring the quantum mechanics. So let's see, here's Feynman's book called QED, Quantum Electrodynamics, The Strange Theory of Light and Matter, Richard P. Feynman, with an introduction by A.Z., the last name Z-E-E-Z. So from Princeton Science Library, here's a book from Feynman. And then what it has here is many nice diagrams about vectorial analysis and the paths photons, particles of light, in the idea, whereas light otherwise may usually be seen to always be just like, how one might say, rays or beams in the intensity of light, rays usually enough. And then about the vectorial analysis and the paths, and he describes the thought process in a summary. So the theory of quantum electrodynamics gave the right answer. The middle of the mirror is the important part for reflection, but this correct result came out at the expense of believing that light reflects all over the mirror, and having to add a bunch of little arrows together whose sole purpose was to cancel out. All that might seem to you to be a waste of time, some silly game for mathematicians only. After all, it doesn't seem like real physics to have something there that only cancels out. Especially if it's non-measurable and it's not observable. So the idea of the virtual photons in the quantum electrodynamics has that as non-observables, it's not scientific. And so it's a way to arrive at a calculating framework, yet at the same time, it's also, for example, from reading from the notes of Feynman, Leighton, and Sands about the Stern-Gerlach apparatus, there are ways to read it then that it's like, well, yes, we've validated our standard model of it, and also open it up that it's not a standard model of it anymore. About the Higgs boson, and that it's a doublet, not a particle anymore. That then this is sort of a count that where Feynman is at least appreciating that this is part of the computing and computational realm and setting of the things, that it's not itself part of the science of it. Let's test the idea that there really is reflection going on all over the mirror by doing another experiment. So all over the mirror vis-a-vis the reflection at the point is about like the extra-local character and aspect of things. So he's describing some more kind of the ideas that go into the reasoning of photons, particles of light, and about there being a finite element analysis, but it's a very, very large finite number that gets involved. Talking about photomultipliers, usual accounts of emitters and detectors, vis-a-vis that nobody's really ever measured one photon or one electron at a time. That's kind of another example of where the instrumentalism and the operationalism of the account is like, well, we're just dealing with whatever we can define as making it observable and immeasurable, something we can sample for the sampling of observation and measurement effects. Vis-a-vis something that has on its own account its own kind of state. And so it's always kind of like this balance of the states between the Heisenberg picture and the Schrodinger picture in these counts. And so this was read up as from the commutation rules and the commutator rules, and then also about the electrons and the finite and infinite, the structures, about that the electrons and the finite and the infinite structures is much more of an account of making it for the continuum mechanics. Because in the account of the quantum mechanics, some might say that the formalism only has the finitistic account. And then as how that made for Fermi holes, and then later for what would make Lienard-Wiechert is after a reduction and abstraction of that, goes to show that the reductionist account is successful and fruitful for coming up with things that then line up with the macro scale and after the mesoscale, the classical scale of things. That the quantum scale of things is yet having these mathematical constructs that are themselves limited by their own accounts of the merely partial or half accounts. And then how to get that so that it is a fuller continuum mechanics, and how, for example, Faraday rotation arrives for Faraday law, because it always is shown to hold. Spiral waves and wave spirals here. These are things that by the time that researchers in quantum dynamics have stacked up all their derivations, there's not much of an opinion that can be had about it. Yet it takes quite a thorough account to have an opinion about these things. And so then when looking in the modern day, there's something like J.S. Bell's inequality, J.S. Bell's account of flux after flow in light. and that it breaks the usual account of the model of here quantum electrodynamics and as after the quantum theory. So that is then a kind of a signpost, and then trying to like backtrack to that, say, okay, it's like let's log our g minus 2 muon or something like that. That's similar in any account of that. It's just like, say, taking a power law and take a power law of that, because that's an easy way out. And then we can end up adding a zero if you look at it from the right direction. And it's kind of like, well, you didn't really add a zero. You just forgot that it was 0, 0, 0 out onto infinity because you already truncated it. So then saying that the mathematical formalism stands that up and then it would be broken otherwise, well, anybody can do that. So the account these days of trying to extend the theory when it's already kind of was designed to not be extended, is truncated, is having then the re-examination of all the stack of derivation and finding where these things are, like Hooke's law in mechanics and Clausius and Arrhenius in particles as for gases, and then about later Planck for these quantum scales, has that each of those is a point to be revisited. And here, as I put it sometimes, like revisit Heisenberg, Hubble, and Higgs. About Heisenberg with the Heisenberg determinacy, Hubble about the account of inflation, which is otherwise a steady state, and then Higgs as for the account that it's not the standard model anymore, and then that's just one of the corners of super-symmetry, and there are others. So supersymmetry again, and flow and flux bring themselves together. Here's Feynman about electrons and their interactions. This is the third of 4 lectures on a rather difficult subject, the theory of quantum electrodynamics. And since there are obviously some more people here tonight than there were before, some of you haven't heard the other 2 lectures and will find this lecture almost incomprehensible. Those of you who have heard the other 2 lectures will also find this lecture incomprehensible, but you know that that's all right. As I explained in the first lecture, the way we have to describe nature is generally incomprehensible to us. So this is arguable. It's an account of like the most confusing thing about nature is that it's understandable at all. It's like the opposite of that is so. And so then trying to what Feynman is referring to is the kind of the suffering of this metaphor that he's carrying out vis-a-vis these things. In these lectures, I want to tell you about the part of physics that we know best, the interaction of light and electrons. That to say he knows it best, that's just an account of how much energy is described as like, well, it's just energy on either side, and then the frequencies, how the frequencies line up, is his own account, and they meet in the middle, but they're coming from either end of it, whereas light just kind of passes right through. So to say that energy and light are the most well known in these things is by definition, and all the derivations are made off of that. So then he says, most of the phenomena you're already familiar with involve the interaction of light and electrons, all of chemistry and biology, for example. So there are many models of chemistry involved here. So besides totally ignoring the account of the nuclear and the radionuclear, but then calling that alpha and beta and gamma, helium nuclei and electrons or anti-electrons, and rays, the Roentgen rays, those being light-like then. Has it again? These are about these tetrads of quantities, where then after the severe abstraction of the electrical reduction, that Feynman's claims for these kinds of things as being so great are in a particular subfield of physics. While that it has great amount of applicability when you can just ignore all the other stuff and just say you're using this to define what makes a circuit or something along those lines, and as for things like lasers and masers, and one being the stimulated intensity of light rays, and the other being just a spallation of electron particles. They're basically 2 opposite things about how that kind of structure after a cavity resonator, both of them are basically employing a cavity resonator. Those are resonances, not they're not particles anymore, and they're not even really so much the waves of the particles; they're resonances. So, Feynman's claims here are a little strong, as I imagine is otherwise his usual manner of not being caught, not getting caught in any kind of way to say that what he's saying is so, because he says, and then nobody knows, and it's like and so sometimes Feynman is considered humorous, sometimes it's insulting, because it's saying that nobody else could ever do something, when really it's just saying that he won't be told any different from what he is doing. So Feynman is humorous, but what we really would need from Feynman is some time where he actually breaks down and says, hey, listen, here's all the things that I would want to say, but you can immediately catch me in a mathematical or scientific error. But these are the things that go into my thinking otherwise, because otherwise he's just saying, you know, for the general audience, this is the way it is. And then for me, the insulting part when he says like mathematics doesn't say anything about it. It's just talk. And whereas for the idea of the continuum mechanics is like that's actually what it has to be. And so the account of the nominalism and the fictionalism is for like the virtual photons and this kind of thing. And then as from reading before, you know, kind of acknowledging in the passage is like, well, if you know that this would necessarily be a point of contention, then you could generously read from me as like acknowledging that without explicitly acknowledging that, makes for it that it's kind of shallow, is usual account. We found out in the first lecture that we have no satisfactory mechanism to describe even the simplest of phenomena, such as partial reflection of light by glass. See this, and this is just sort of a count. It's like, well, there are all the different ways, and then the idea of that, then having to get them to agree is another sort of account. We also have no way to predict whether a given photon will be reflected or transmitted by the glass. All we can do is calculate the probability that a particular event will happen, whether light will be reflected in this case. So this is saying all we can do is kind of the royal we, you know, saying that that's so for everybody, and it's not so for everybody, because there's a continuous quantum mechanics. For example, as Max Born mentions later in his work, he's like, this is why the infinite self-energy and the like of why there's a continuous interpretation of quantum mechanics is always there. And then, and indeed, Feynman in some of his other works addresses that a bit more closely, like the description of the Stern-Gerlach apparatus. And again, though, just not like quite coming out and saying it, that that's what the physics really is, instead saying this is what our focus is. So Feynman's theory is more of a computational setting than an explanatory or fundamental theory. It's an experimental approach, not so much the theoretical satisfaction. That said, it then is then quite thorough about just the ideas of what would be the measurables, and then how we can diagram these things, and what they would look like, and assigning variables vis-a-vis time, a certain time t. The event whose probability we're calculating is the detector at A makes a click at a certain time t on the space-time graph. And so it does include then the idea of the space and the time, the entelechy of the things, the continuum. So yeah, this book is then is kind of lectures collected as describing quantum electrodynamics. Here's a footnote. He says, it's very unfortunate for us that Newton convinced himself that light is corpuscles, because we can see that what a fresh and intelligent mind looking at this phenomenon of partial reflection by two or more surfaces has to go through to try to explain it. In parenthetically, he says, those who believe that light was waves never had to wrestle with it. Now, that's not so, because everybody who's trying to figure this out in the field, and the whole idea of particle-wave duality always has this as so. Talks about Newton and his corpuscles versus like Fresnel and Huygens and waves, vis-a-vis Fizeau and just the velocity. And then that gets into things like besides things like Michelson-Morley, or I'll often say Michelson-Morley, but I sometimes hear it Michelson-Morley, the idea that it never shows up in the frame that the light's wave would be retarded, because then it would have to invoke something like FitzGerald space contraction to explain why it just cancels out. It's kind of like when Feynman says, like, why would we do all this stuff just to have it cancel out? And part of it is like, well, so then you can cancel out the whole idea of space contraction actually really canceling things out. So the very setting of making something that is a constant and fixed and not moving, and then also as the account of its velocity. And then with regards to things like then light and how it's supposed to behave in terms of whether it's attached to something or it's just free. And here the usual idea is that light is free, and so it's free information. And so that thusly there are ways to address both the usual experiments of general relativity and then the usual experiments of quantum mechanics, and then also to get into how they can agree. Because otherwise, it's well known, the crisis in physics today, that quantum mechanics and general relativity, their usual accounts don't agree to 120 orders of decimal magnitude, which is much too large a number to call it correct. The idea made use of the fact that waves can combine or cancel out, and the calculations based on this model match the results of Newton's experiments, as well as those done for hundreds of years afterwards. Then there are experiments where they don't cancel out, like the Arago spot. It's like, the conscientious scientists can't ignore any of the data, even if it's not part of their experiment. They might want to make accounts for whether there's controls for the experimental setting and the scientific theory. But this account of the practical and applied as it may be is again limited to a particular subfield of physics. And furthermore, the objects of which it intends to describe is not complete. So that's usual. And of course, it's possible to just go on forever and under these sorts of accounts, because this kind of thing. Here he says, that exposes all the problems associated with quantum electrodynamics. Even though we have to resort to a dippy process to calculate J today, it's possible that someday a legitimate mathematical connection between J and E will be found. That would mean that J is a mysterious number, and from it comes E. In such a case, there would doubtless be another batch of papers that tell us how to calculate J with our bare hands, so to speak, proposing that J is 1 divided by 4 pi or something. So that's about Planck and the account of Planck's constant, and why what that is to be made as an example of something changing in the classical. So that'll follow some more later to be considered. But it is about why then for this, in physics a lot of times it'll show up these spurious factors of 2 or 2 pi or pi. So here that's about the measure theory in itself and the doubling and halving spaces, and why what would otherwise just be everything's classical and linear, why it's super classical and quasi-invariant vis-a-vis the invariant theory, which dictates all of quantum mechanics. It's causal efficacy in the formalism. It has that there are real aspects of mathematics, the re-Vitali-ization of measure theory, to help solve these sorts of accounts of the measure problem and help explain why the factors that are spurious yet can be argued to show up like from accounts of reflection. It's like, well, we're taking either half. Why not 2? Meaning that they would just fall out on the side later in these cancellations, as Feynman puts it. Or as Wyeth's like to show, that these things can be sorted out and figured out. And he talks about the renormalization, so the normalizable theories, which is after an account of Born, is where it's so that then trying to figure out for the inversions of these things that are very, very small, they'd be infinitely large. And so it is a continuum mechanics, and it needs mathematics, infinity and continuity to figure it out. And the fundamental superclassical results that make it so that it's a mathematics and not more of just a descriptive account. That the mathematics does the work. So these are the issues. It's surprising that the theory still hasn't been proved self-consistent one way or the other by now. I suspect that renormalization is not mathematically legitimate. It's under its own account. What is certain is that we do not have a good mathematical way to describe the theory of quantum electrodynamics. Such a bunch of words to describe the connection between N and J and M and E is not good mathematics. Then he has a footnote. Another way of describing this difficulty is to say that perhaps the idea that 2 points can be infinitely close together is wrong. The assumption that we can use geometry down to the last notch is false. So here the idea is that in the infinitesimal and small, there's what's called geometric mutation. And so this is like, well, is it a square or is it a circle when it's crushed or approached infinitely precisely? Or mass, length, and time and distance, do those that enter then like a setting where they become, this is the curled up in the dimensions, sometimes it's called in the superstring theory. So this belies the behavior of the infinitely divisible all the way down. So the model of the complete ordered field, the mathematical idea that's usually given as the formalization of the real numbers, the linear continuums, numbers as they would be, by magnitudes as numbers, has that then these other models of real domains, the line reals, then the field reals, so giving least upper bound and measure 1.0, something for the field reals to have, because otherwise they don't, it's axiomatized. And then for the signal reals, coming back the other way, makes it so that for Feynman, this is something that he's like, it's never going to happen because that's not mathematics. It's not mathematics anymore for that to be so. And the actual point is that it is mathematics, and it's super classical mathematics, and it is relayable if involved. Then for something like the account of the continuous domains and the measure problem is that it involves that it's a continuum mechanics, and it's replete in this sense. So here before I was complaining that Feynman wasn't upfront with the problems, and so here he's being more upfront with the problems. Immediately, you would like to know where this number for a coupling comes from. Is it related to pi, or perhaps to the base of natural logarithms? Nobody knows. It's one of the greatest damn mysteries of physics, a magic number that comes with no understanding by man. The amplitude for a real electron to emit or absorb a real photon. Then the idea that that's mathematical. My physicist friends won't recognize this number because they like to remember it as the inverse of its square, about the defined structure constant with an uncertainty of about 2 in the last decimal place. It's been a mystery ever since it was discovered more than 50 years ago, and all good theoretical physicists put this number up on their wall and worry about it. So this is making for accounts of, much like O.W. Richardson and the electron theory of matter. So that predates Feynman here by about 40 or 50 years at least. Has that there are different ways to look at the constant C, and then there are different ways to look at electrostatics, electrodynamics, and light with regards to the constant C, and they differ. And indeed, in fact, according to the formalisms, one slightly greater than light's and one slightly less the other way. And so then they're all reduced to C, but and the theory is only like to the first order term. So that's another example of then what's going on. And then when it gets to like these things having been lined up, is that they were crushed together to make a sandwich of it. And really they are coming and going, and it's only like the one going both ways infinitely at once, even something in the middle that the other is just as track, is kind of an account for then two things. One is the idea of the Pauli principle being broken apart, because the Pauli principle is like two particles are either alike or they're different, and they are distant. The other one is like, well, what happens when they touch and come together, or when one breaks apart, like a cell dividing, or something like that. Or for boundaries, this is usually put in Brentano and boundaries, the reductio and the logic about it. So Feynman says is like, well, what happens when it happens is are they both going towards the middle, or is one breaking away from the other? And each of these three different accounts makes for these sorts of accounts. So the other one is about the cube wall, and it's like, well, how about inverse square? As long as we're still trying to figure out the fine structure constant, it's like, what's up with inverse square? And why does that work for things like the Keplerian and Newtonian and equal area and all this kind of stuff? That then these get into the various kinds of pieces that are part of the formalism, regardless of what everybody's been able to make of them, given that everybody, in the most part, is already stuck with one particular perspective that isn't always the one with the best view. So the optics could be better. But it is appreciated by the time you get to the end of Feynman's book, he's saying, before you leave, don't just call me wrong. I'll try to make some apologetics here. There's also the problem: what holds the neutrons and protons together inside the nucleus? So besides the hadron physics and the gluons and the account of quarks, then there's a whole account of the nucleonic, which is just a totally different way of looking at a nuclear model of the nucleus. And that's much more lined up with like the isotopes. It's like, the periodic table and how it's great, and it's got like according to electron orbitals, it's got a great organization of the things, and then by the atomic number, at least the atomic number is the same, and then the isotopes are just by the masses and the weights of the atomic masses. And then we tell that about the electrons and the kinetic. We say that that's all belongs to Higgs and is called the unification energy of it, which basically means we don't know anymore. Then instead, the nucleonic account is just like, it's like a straight line of the isotopes and the masses together. And so it's basically a straight line by the mass, and then the different isotopes kind of spin around that line. So it's a different kind of periodic diagram, instead of one that's being like a periodic table of like, these are the outermost electron orbitals that define inorganic chemistry's covalent bonds, simply enough. Then it's a periodic table that's really more or less just like a line. So there are at least two entirely differently centered nuclear theories. So the problem that Feynman has is like, the problem is he didn't know he had two problems. It was realized right away that it could not be the exchange of photons. Though as massless and charged particles, it could be. You could just say they're virtual nuclear photons. Because the forces holding a nucleus together were much stronger. The energy required to break up a nucleus is much greater than that required to knock an electron away. So this could be considered just kind of like the space inversion and making for the account of the tetradic quantities, why there's the four fundamental particles: neutron, electron, photon, proton. And then similarly, as for the accounts of the forces, there's usually the strong nuclear force, and then the electrical force, and then weak and electroweak. Those being kind of either way, just kind of making for a tetradic quantities. This tripartite account of the relations. That it could be instead like the nuclear force, and then like the weak and strong kinetic, or the weak and strong charge. Any of those can be split about in different ways. It just has that in the account of time in the universe, that most of that's done according to massive bodies being very, very slow, and electrical current being very, very fast, compared to like light speed being infinite and nuclear lifetime being eternal. So that said, though, they could be still rephrased in this wider sort of account. So then that's for somebody who's studying this thing. So Feynman says, so there you are. Quantum theory has three main types of interactions: strong interactions of quarks and gluons, the weak interactions of the W bosons, and the electrical interactions of the photons, which are massless and chargeless. So quantum electrodynamics, then related to quantum chromodynamics, has their basically descendants, one after the other, or vice versa. And then it's not the only game in town by far. Let's see, what's this book? It's from the International Series of Monographs in Pure and Applied Mathematics, Introduction to Set Theory and Topology. So this is Kuratowski. So Kuratowski would probably be most famous for the graph, the completely connected graphs, which above K2 are non-planar. although they could be described as planar by introducing crossings as making a graph that you can take any graph and draw it on paper. It's just you have to disambiguate which are crossings and which are connections according to the projections. Put this aside for a second. And then, because this box is not all quantum mechanics, but I'll hope to find some more about it. Dispersion theories of strong interactions at low energies. So this is Shirkov, Serebriakov, and Meshcheryakov from Wiley Inner Science. Used to be a library book at the University Library from QC 794 S4913. Dispersion theories of strong interactions. From Cal State Poly, California State Polytechnical College. Withdrawn. Dispersion theories of strong interactions at low energy. So you got high and low energy, and then weak and strong, near and far, and these sorts of accounts. And what they're meant to address is that when things happen at the interfaces and the boundaries, the change. It's like shear from the accounts of turbulence, and these kinds of things. So it's then accounting for things as weak and strong and near and far and high and low energies. R is about that. Then here it's almost universally an account of flow. This being the usual bulk, aggregate, and flow, and flux, which is tentatively everything's just kind of like in suspension of that. So flow and flux are here that the weak and strong basically make for an account of fortitude, near and far an account of distance, and high and low an account of scale or this, and then that flow and flux make an account of direction. So then the idea that there's always both directions is otherwise always the usual account is given as like there's only one direction, the way the thing is going. But there's always for the potentialistic account that is everything about the outsides of that. So for example, if you think of like a ball or a donut or a torus, and there's a flow going around it, and then to go into it, it has to come out from around it and back the other way. So that's the way to look at the idea of flow and flux. And then flow and flux are to be distinguished a little bit in the terms, because you'll find them, they're already, of course, very well defined and used in other fields. And the idea is they stay that way too. And they do, because then for the supersymmetric aspects, they're attached to these different areas, at least one of which is where flow and flux are the same. It's like, what's the definition of flow? Well, it's the passage of things. It's the bulk and the aggregate, the passage. What's the definition of flux? Oh, it's the same definition. But then at these corners is where it's like, well, what's the flux for J.S. Bell's aspect and Ellen aspects types experiments? Well, it's going the other way. Or what's the flux with regards to when we're looking to examine a particle, and then as it gets infinitesimal in the geometric mutation, what's the flow the other way? It's like, well, it comes out in every direction. Or for Einstein, when we talk about the mass-energy equivalency and how it's built up first as an account of kinetic energy according to a direction, that later his whole account of Einstein's bridges, well, here's one that's centrally or radially symmetric. So flow and flux are key in any account of, then these accounts, when they get talking about weak and strong and near and far and high and low, have that. These are the accounts where it's otherwise just be like, it's near and it's strong and it's high, and it's far and it's weak and it's low. Those are the usual counts. Nobody would care then to even introduce those words. You wouldn't need them. You would say like either large or small. But when you cross them these ways, so this is the strong interactions at low energies is about the emergence, and then after the convergence, the emergence of the behaviors of what would otherwise be, according to induction, not so, the anti-inductive results and accounts. So that way then for something like in the hadron physics, for example, they call it asymptotic freedom, because all the particles of the nucleus are you figure if that was a strong force in the center, they'd be held on with the most strength of that force, because it's defined by, like the account of Schwarzschild or Chandrasekhar, the Schwarzschild radius, within which everything is the same infinite density. Asymptotic freedom it has in the middle is like they're always rolling around and spinning around in that, and that's was predicted. It's given in the theory, just like the Arago spot comes around and shows a little dot in the backside of otherwise the shadow of the light to a globe or something like that. It's always everywhere. Then or for Feynman's account of his mirror, he's like, well, the rest of the mirror, and these kinds of things. That here, this account of the asymptotic freedom is for the anti-induction, and it's a super-classical account of flow always having an anomaly non-zero opposite flux, and then when it happens that those are compounding and going together, like the resonance is when flow is a resonance besides a wave, say. So these are the sorts of counts. So then, a couple weeks ago, we were reading from Fritz London about the superfluidity. And so that, of course, is where a lot of these things come into play, because otherwise, when we're talking about electricity and it having like a liquid model vis-a-vis a fluid model, has that liquids behave as flowing within their containers. And electricity behaves as flowing within its container. So they both have a fluid model of the flow. Yet, when it comes to that, like static charge holds up, and it can be of infinitely high value, yet 0 amperage behind it, the potential difference vis-a-vis the electromotive force, the skin effect and the core effect of electricity and liquids are opposite each other. So on one hand, one account of the commonality, they're the same, but then in the extremes they flip. And so it's a way to account that with superfluidity and the like. I was like, well, when it goes to 0, then some of these things that were functions otherwise of like resistance in an electrical circuit, now that's gone to 0. It's going to make a standing resonance of this automatically. And then to count for then what that does in the quantitative, both at the limit or beyond these limits of the boundaries, and then through the layers, the turbulential layers of these things, is a thing. There are 2 counts of things that would happen if one were to find a black hole, gravitational singularity to the event horizon inside the Chandrasekhar limit, or about the Chandrasekhar limit, inside the Schwarzschild radius. What would happen to any object that reaches the event horizon? One is that it gets spaghettified, meaning it's entirely disincorporated. It is destructed. And the other one is that nothing would happen. So then the ideas of these layers and these kinds of things are about these kinds of counts. So let's take a look at this book then and see what it kind of has to suggest is what's going on. Because what it'll be describing is what is called effects in physics, where effects are things that are just not described by the theory, but are so. So from nuclear research, 1969, North Holland, Wiley Inner Science. The method of dispersion relations during the past 10 years of its existence has occupied an important place in the theory of the interactions of elementary particles. So dispersion relations are among reasons why I mentioned Fritz London, because today the intermolecular forces of bonds are defined in terms of London's dispersion forces as much as classical Tinker-Toy models of bonds. Opposites, one super-classical, the other. One the more potentialistic account that adds up in the end to the same thing as a classical account, because the classical account is just a potential realization. This method has found applications in all the basic aspects of the theory, such as strong and weak interactions in the regions of both low and high energies. Very recently, it has been playing an important role in the development of a new approach associated with symmetries and current algebras. So Virasoro, Virasoro, something to suggest. In this book, an attempt is made to give a consistent presentation from the point of view of applying the method of dispersion relations to the problem of strong interactions at low energies. First two chapters survey the basic concepts of the method, beginning with quantum mechanical considerations on the problem of scattering, going on to a specific application to low energy region. So scattering is the idea is like, well, how things are going to emit and go radially symmetric and then be omnidirectional. Vis-a-vis the tunneling is like, well, that's happening between two electrodes. Eventually they're going to arc and it's a perfect straight line between them. Or like however it goes through that according to Faraday rotation and the Faraday effect. The fundamental presentation proceeds from equations for lower partial waves obtained with the aid of the differential approximation. The process is of pion-pion scattering, photoproduction of pions on pions, pion-nucleon scattering, so the electromagnetic form factors of pions and nucleons are considered by this method. So this is a nucleonic account, and so the whole subfield of quantum chromodynamics and hadron theory and Higgs theory just doesn't know anything about it. It is quite natural that with such a methodological approach, some important investigations in the strong interaction region at low energies proved to be beyond the framework of this book. Yeah, there are limits to there. It needs to be figured out the emergence after the convergence, because when those are super classical, then all the partial accounts of convergence can say is like, well, I'm possibly not wrong, and I've checked that my solution applies, and now let's put in the numbers and never mind. Now, as the authors put it, beyond the framework. The authors go on. This may also be applied to the survey part, which claims only methodological completeness, beyond the framework. We believe the description of a completed stage of the development of the theory is of some interest, and that's what we're talking about here, kind of. Being useful not only to a narrow range of scientific workers, but also students and postgraduates, as well as experimental physicists working in the strong interaction domain. So theoretical physics, the Laboratory of Theoretical Physics, Mathematical Institute, Academy of the Sciences, these kinds of things. This is something that I'll be looking at for a while. So the dispersion method in quantum theory, problem of scattering in quantum mechanics, dispersion relations, unitary conditions. So you got unitarity, complementarity, and orthogonality. All these are usually generally given to hold. And then what happens when things start letting out, then there's like, well, which one of these we're going to let out, because they're all supposed to hold. And so unitarity, complementarity, and orthogonality all do hold in the affine and the conformal. So it's a continuum mechanics to explain why, well, there are spiral waves and wave spirals that explain why these frame spaces and space frames have real space contraction linear and space contraction rotational. All these things. Double spectral representation. So it's bad enough when already spectroscopy has made it so it's like, well, what's quantum mechanics? It's like, well, it's discrete quantum mechanics. Vis-a-vis continuous quantum mechanics. And there's another one that says, well, like, okay, we got a spectroscopy, so now it's great. We have a successful spectroscopy and a successful discrete quantum mechanics, and here's a Zeeman effect. After Faraday effect, about 80 years after that, about the magnetizing the light in the media and these kinds of things. It's like, great, so we got spectroscopic account. And then it's like another one's like, well, we have two of these approaching each other, and now they both have spectroscopic accounts. And now, kind of like with the ideas of the rational radical magma algebras, or vice versa, and the null-Stellensatz and these sorts of accounts besides, have that this is a double spectral representation getting involved. So let's take a look at that and see what it tends to describe. Chapter 2 is, so if Chapter 1 is the dispersion method, Chapter 2 is some general ideas on low energy approximations, unitarity conditions, low energy equations, Cini-Fubini approximations, Chew-Mandelstam, mentioned in multiple times, CDD singularities, resonances in the neutral model, resonance solutions of the neutral model, equations for pi-pi scattering, pions. Chapter 4 is the electromagnetic interaction of pions. Chapter 5 is the pion-nucleon interaction. Chapter 6 is conclusions and summary. So yeah, this is a field of physics. It's its own subfield. It's called nucleonic theory, and it's not hadronic theory. but it is very well supported by large amounts of data at high energies. So, double spectral representation. The analytic properties of the scattering amplitude, as for a quantum amplitude, with respect to delta squared and k prime, may be fully investigated for a superposition of Yukawa potentials. V equals V naught times this integral from mu naught to infinity of sigma zeta times e to the negative zeta r over r d zeta. For example, the second Born term of the scattering amplitude for Yukawa potential, sigma zeta equals delta of zeta minus mu, or as for the Dirac delta, usually that would be, has the form t squared of k big delta squared equals m squared v naught squared, integral from negative 1 to 1 by dy of 1 over this term gamma y mu squared minus 2ik lambda y. So wave function constants vis-a-vis means. So it's putting together things to do with probabilities and waves and Euler's identity and about the convolutive setting all in one little equation. So the derivation has this it's a doubly spectral account of the doubly spectral account here is what's going on. This expression is analytic in the upper half K plane. So the other day I mentioned something like Wigner's account of the semi-infinite, but it's Witten's account of the semi-infinite. That the identity dimension discussed here earlier is about trying to figure out how to set up more convolutive settings about the coordinate treatments. That this stuff is all built after is like, well, remember in first grade when you learn the number line, it's like, okay. In seventh grade when you learned Cartesian coordinates in the XY plane, yeah, sure. It's like, well, and then by the end of that, somebody says, well, we're just going to tack a complex plane on top of that. It's like, well, yeah, I get it. Well, now, remember when you first learned the plane and the quadrants are labeled 1, 2, 3, 4? And so you can just say, well, what about just that quadrant 1 of the non-negative or positive numbers? And now just draw a line through the middle of that. Now, if you had to work in that, on the one hand, you kind of have to unlearn that the other stuff is always there. But on the other hand, it's like, well, then you can just figure which side of the line it's on. So, like here, when it says, for example, negative 1 and 1, you know, it's that's about the same kinds of things. So Witten's half plane and the identity dimension, and here the being analytic in the upper half K plane, if delta squared is greater than negative 4 mu squared. So about the bounds of what would be this probability amplitude, and then for triangle inequality and Cauchy-Schwarz. All together, all these different aspects of windowing and boxing the things to make an analytical setting. This is what's going on. This expression is analytic in the upper half K plane. Therefore, the formula can be represented as t to the second here equals the integral from 0 to infinity of dk prime squared over pi which is funny to see in an integral, like to see the differential term squared of w k prime squared comma delta over k prime squared minus k squared minus I epsilon. So the k prime squared minus k squared minus I epsilon kind of reminds of, after these quantum amplitudes, there's a lot of doubling and squaring and roots going on, because then it's figures like, well, that just leaves the real analytic part, and then after squaring it, because it was negative and now you squared it, so now it's positive, or it had a complex number in it, and so you squared it, now it's like so. And the identity dimension is kind of like, well, it's always square. These kinds of things. That this is then another number that would bring the Boltzmann constant pretty readily, or a reason for why that doesn't have Planck's constant there, because it's just used in e to the IH everywhere for Euler's identity to model rotations as another aspect of these things. These formulas are very, very involved and dense and in an arbitrarily deep stack of derivations already when trying to pull these things apart. And then carrying on then, if there's a few more minutes here or less in this talk, getting into then it's written, and then to get out the imaginary part, and what that equals is, and so he's like, so what we're going to do now is, if that's the real part, we're going to take the imaginary part on the side and give it an account of how it's some squares in a small boxed or bounded region. It's to be windowed. If it's going to be windowed and boxed to make it analytical, to give the account of the analyticity of the mean, and then as after this constant again, because that would be complex, so it'd end up being between 0 and 1, basically, or between 0 and 2, so that its squares between 0 and 4, or vice versa, between 0 and 4, so that its roots are between 0 and 2. This integrand will be rewritten as ... and it's factored out 1/4, and it's made then in 1 minus y squared, adding the convolutive setting back before. It's like, well, it's these two variables, x and y, and they're to make a square, and so we're going to bring them back down the line by having this as, and now we can just call it minus instead of divides. So this kind of sleight of hand in a sense. If now in 2.25 we integrate over y, we have the imaginary part brings this. This relation defines the analytical properties of the imaginary part of t squared, or t to the second, of k delta squared with respect to the delta squared variable. More precisely, the imaginary part of t to the second power, k delta squared, is an analytic function of the variable delta squared in the complex delta squared plane, cut along the line delta squared threshold equals mu squared plus 4k squared over k squared less than or equal to delta squared less than infinity. So after an account of space inversion and then identity dimension, that can also be describing what's going on with this sort of formalism vis-a-vis the spectral and the doubly spectral, or for an account of how then these two rational approximations, like it's a great matrix of orthogonality and unitarity and complementarity for things like the convolutive setting after the involutive setting, essentially. And then when it all points to a point at the end, they what were orthogonal become and perpendicular become parallel, which is what's happened. Well, all right then. Point being about this is that nuclear theory is at least two theories, and in quantum electron dynamics and quantum chromodynamics are kind of one or the other in front of the other. And so having defined quantum chromodynamics kind of after quantum electrodynamics does not really provide a way back. And then otherwise it will just all start looking like a power law. And so modern accounts of stuff like the and this is just kind of one of my personal opinions about the G minus 2 muon is just writing a zero where there's nothing except what a zero could be, anyways, in theory. Hey, have a great day, gentle readers. A rainy day today. Rainy. Here is about the nucleons and the nuclear theory, and then for a spectral account of orthogonal spectricity or something like that. Good day. Goodbye.